Hello everyone, this is Kalpana here. In this video we're going to see a problem, not a problem, few problems from conformal mapping. So let's get going. In this video we are going to see bilinear transformation, problems on bilinear transformation. Well, a transformation or the transformation omega or w, whatever you call, omega equal to az plus b by cz plus d, where ad minus bc is not equal to 0. A, b, c, d are complex constants, is called bilinear transformation. Okay, and this is the formula we'll be using to find bilinear transformation. Okay, let's begin. Problem: find the bilinear transformation which maps the points z equal to 1 minus I 0 onto the points omega equal to 0 to minus I. Okay, so we are given points z and omega. Consider these 3 points as z1, z2, z3 and this as omega 1, omega 2, omega 3. Okay, given z1 equal to 1, z2 equal to minus I, z3 equal to 0 and omega 1 equal to 0, omega 2 equal to 2, omega 3 equal to minus I. Okay, the bilinear transformation is given by omega minus omega 1 into omega 2 minus omega 3 by omega 1 minus omega 2, omega 3 minus omega. Okay, in the same order we'll write for z on the RHS. Okay, z minus z1, z2 minus z3 by z1 minus z2 into z3 minus z. Okay, just substitute the values here. We'll get omega minus omega 1 0 into omega 2 2 minus omega 3 minus I by omega 1 0 minus omega 2 2 omega 3 minus I minus omega equal to z minus z1 1, z2 minus I minus z3 0 by z1 1 minus z2 minus I into z3 0 minus z. Just simplify it. We'll get omega minus 0 omega into 2 minus into minus plus I by minus 2 into minus I minus omega equal to z minus 1 into minus I minus omega 0 is minus I, right? So you'll get minus I 1 minus into minus plus I into minus z, right? Now see how you're having minus 2 into minus I minus omega. Take minus common from these two terms, you'll get minus 1 into I plus 1. Minus 1 into I gives minus I, minus into plus minus 1 into omega, omega, right? Again, minus 2 into minus 1 is 2. So you can write this as minus 2 into I plus omega. So the denominator of LHS can be written as 2 times I plus omega, right? And here you are having, consider this part, minus I by minus z. Cancel this minus, you'll get I by z. Or you can treat this minus I as minus 1 into I and minus z as minus 1 into z, and then minus I by minus z can be treated as this, right? Where you can cancel minus 1 from the numerator and denominator, you'll get I by z. Okay, so you'll get z minus 1 by, okay, into I by 1 plus I into z, right? Fine. Now make a cross multiplication. Just simplify this numerator. Multiply omega to these two terms, you'll get 2 omega plus I omega by multiply 2 to these two terms, you'll get 2I plus 2 omega equal to, here also just simplify it, okay? IZ minus 1 into II by 1 into ZZ plus I into ZIZ. Okay, now make a cross multiplication. You'll get 2 omega plus I omega into Z plus IZ equal to IZ minus I into 2I plus 2 omega. This gives us 2 omega into Z, 2 omega Z plus 2 omega into IZ, 2I omega Z plus I omega into Z, I omega Z plus I omega into IZ, I into I square omega Z equal to IZ into 2I, 2Z, I into I square 2Z, IZ into 2 omega is 2I omega Z minus into plus minus I into 2I, 2I into I square minus into plus minus I into 2 omega is 2I omega. Okay, fine. Since I square equal to minus 1, you will have to remember this, I square equal to minus 1, okay? And this gives us 2 omega Z plus 2I omega Z plus I omega Z. Yeah, here 2I omega Z plus I omega Z gives 3I omega Z. Okay, plus you having I square. Replace I square by minus 1. Here you having I square. Replace I square by minus 1. 2I omega Z minus 2 into, replace this I square by minus 1. Right? This gives us 2 omega Z plus 3I omega Z minus omega Z equal to minus 2Z plus 2I omega Z plus 2, minus into minus plus 2 into 1, 2 minus 2I omega. Right? Fine. Now bring all the terms which involves omega in RHS and write the terms that does not involve omega in LH. What I'm saying, bring all the terms that involves omega in LHS and write the terms that does not involve omega in RHS. Okay, so we are going to bring this term and this term to LHS. So you'll get 2 omega Z minus omega Z gives, let's simplify here also. Okay, 2 omega Z minus omega Z gives omega Z plus 3I omega Z. Now bring these two terms to LHS. This plus 2I omega Z becomes, it's I, okay, becomes minus 2I omega Z, and this minus 2I omega becomes plus 2I omega, right? So here we have 2 and minus 2Z. Okay, here we wrote all the terms that involves omega, and here we wrote the terms that does not involve omega simply, right? Now see, you can simplify. 3I omega Z minus 2I omega Z gives I omega Z plus 2I omega equal to minus 2Z plus 2, right? Now observe carefully. We'll take omega common here, okay? We can take omega Z common from these two terms. You'll get omega times Z plus IZ plus omega times 2i. I can write this 2i omega as omega times 2i, right? And RHS remains the same. Let it be. Now, you can again write, take omega common from these two terms, you'll get omega times z plus iz plus 2i equal to minus 2z plus 2. Right? Now, take this term to RHS because it does not involve any omega, right? Only z's and I. Just take this to RHS, you'll get minus 2z plus 2 by z plus iz plus 2i. Okay. Now, I'm going to simplify the denominator, or you can simplify first and take to the denominator of RHS. Right. Now let's take z common from the first term. You'll get z times 1 plus I plus here you'll get 2i equal to minus 2z plus 2. Now take this term to RHS, you'll get w equal to or omega equal to minus 2z plus 2 by z times 1 plus I plus 2i. Okay. So which is the required solution, you can say, which is bilinear transformation. We are asked to find bilinear transformation, right? Which is a bilinear transformation, where just compare this with the formula omega equal to az plus b by cz plus d. You'll have a, which is minus 2, quotient of z, right? A is quotient of z, which is minus a, plus b equal to 2, c, quotient of z in the denominator, c equal to 1 plus I, and d equal to 2i. Okay, fine. This completes the problem actually. Okay, let's see whether the answer is correct or not. How you'll check whether the problem is correct or not? Just substitute the values of z, then you'll get the corresponding omega value. Okay, we'll see that. I'll show you for one problem. Now let's see verification part. We'll check whether our answer is correct or not. Okay, the transformation is correct or not. Fine. This is our transformation. This is the transformation we got, right? Let's substitute the values of z1 and see what we are going to get. See, z1 equal to 1, right? Just substitute it. You'll get minus 2 plus 2 by the denominator, right? Which is 0 by 2i plus I, 3i plus 1. 0 by anything is 0, right? 0 by any number. This is a complex number, right? Which is 0. Or you can write it as 1 plus 2, 3i. A plus IB is a complex number, okay? Fine. Now, complex number is of type A plus IB. Is of the form. Complex number is of the form A plus IB. Fine. So, when Z equal to 1, you got omega equal to 0. Let's see what happens if we put Z equal to the next number. When Z equal to minus I, two I plus 2 by minus I plus minus into plus minus I square plus 2I, which gives us 2I plus 2 by 2I minus I square is minus of minus 1, which gives us 2I plus 2 by 2I minus I is I, right? Just I. Minus into minus plus 1. Take 2 common from the numerator. You'll get 2 times I plus 1 by I plus 1. You can cancel out the complex number, then you'll get 2. So when z equal to 1 you got omega equal to 0, and when z equal to minus I you got omega equal to 2. Let's see the last one. Just substitute z equal to, yeah, you have a transformation, z equal to 2i plus 2y, z times 1 plus I plus 2i equal to minus 2 into z equal to, for z equal to 0, 0 into this term is 0 plus 2 by 0 into this 0 plus 2i, which gives us 2 by 2i. Now multiply and divide with I. You will get I by I into I square, since I square is minus 1, which gives us I by minus 1 is minus I, right? So when z equal to 0 you got z equal to 1 you got omega equal to 0, when z equal to I you got omega equal to 2, and when z equal to 0 you got omega equal to minus I. So the transformation is correct, right? So I'm giving the conclusion that therefore the required bilinear transformation is omega equal to minus 2z plus 2 by 1 plus I into z plus 2i. Okay, I'm writing in this form: a z plus b by c z plus d. Okay, fine. So this completes one problem. Let's see another problem. So here is the second problem. Find bilinear transformation that maps z onto the points omega. Okay, let's see. I'm going, given z1 equal to 1, z2 equal to I, and z3 equal to minus 1, and omega 1 equal to I, omega 2 equal to 0, omega 3 equal to minus I. The bilinear transformation is given by, you'll just write the formula. Omega minus omega 1, omega 2 minus omega 3 by omega 1 minus omega 2 into omega 3 minus omega equal to, just in the same pattern we'll write for z, z minus z1, z2 minus z3 by z1 minus z2 into z3 minus z. Okay, let's just substitute the values. You'll get omega minus omega 1 I into omega 2 0 minus of omega 3 minus I by omega 1 I minus omega 2 omega 3 minus omega equal to z minus z1 z2 minus z3 by z1 minus z2 into z3 minus z. Just simplify it. You get omega minus I into 0, minus into minus plus I, will just get I by I minus 0 is I into minus I minus omega equal to z minus 1 into I minus into minus plus 1 by 1 minus I into minus 1 minus z. Okay, see, you can take minus common from these two terms and from these two terms, right? Since you're having minus I minus omega minus 1 minus z. See, minus I minus omega can be written as minus of I plus omega. Likewise, minus 1 minus z can be written as minus of 1 plus z. Okay. Now, multiply the numerator with this I, you'll get omega I minus, yeah, you can just cancel this I, right? Waste of time. Just cancel out this I, you'll get omega minus I by minus of I plus omega equal to z minus 1 into I plus 1 by 1 minus I into, take minus common. If you take minus common, you can just write it as minus can be written as minus 1. So you can write it as minus 1 into 1 plus z. Okay. Now we will write this term by minus this term as minus of omega minus I by, you can write I plus omega as omega plus I equal to, here also we'll write like minus of, okay, you'll take this minus outside, so you'll get minus of z minus 1 into I plus 1 by 1 minus I into z plus 1. 1 plus z can be written as z plus 1, right? Now you can cancel out minus 1 or multiply both sides of the expression with minus. Or see, in the denominator you're having 1 minus I, right? Likewise, you'll write this I plus 1 as 1 plus I. Just we are trying to write in one format, okay? Just multiply both sides with minus, you'll get omega minus I by omega plus 1. It's I, right? It's I, I'm sorry. It's I, not 1, equal to z minus 1 into 1 plus I by z plus 1 into 1 minus I. Now, we need to find bilinear transformation, which is of the form omega equal to az plus b by cz plus d. So here we have omega minus I by omega plus 1. So it's hard to find omega, just a single omega equal to this fraction, right? So what we'll do is we'll just apply componendo dividendo rule. Is when a by b, if a by b equal to c by d, then a plus b by a minus b equal to c plus d by c minus d. Simply we'll add, here we'll add these two, and in the denominator we'll subtract b from a. Okay, a plus b, here comes a minus b, here we'll add and here we'll subtract. Okay, add, subtract, add, subtract. Just apply that. You'll get omega plus I plus omega plus 1. Is it 1 or I? It's I. I'm always writing it as 1. Please be very careful while writing the numbers. And in the denominator, we'll subtract the two numbers. Okay. Here in the numerator, we'll add the two numbers, and in the denominator, we'll subtract. Z plus 1 into 1 minus I by z minus I, sorry, z minus 1, 1 plus I minus z plus 1 into 1 minus I. Right, this gives us omega minus I plus omega plus I by omega minus I minus omega, minus into plus minus 1 into I equal to, simplified, you'll get z plus iz minus 1 into 1, 1, minus into plus minus 1 into I plus z plus 1 into 1, z plus 1 minus z plus 1 into I, zi plus into minus minus 1 in z into I, what I'm doing, z into I, zi, you got minus, plus into minus minus, z into I, wait, z plus 1 into 1 is z plus 1, right, minus z plus 1 into I is minus zi minus I. Okay, z into minus I is minus zi, 1 into minus I is minus I. Fine. And here in the denominator, z minus 1 into 1 is z minus 1 plus z minus 1 into I is z into I, zi, minus into plus minus 1 into I minus of z plus 1 into 1, z plus 1, minus into plus minus z into I, zi, plus into minus minus 1 into I. It's not complicated, you just need to focus. Cancel out minus I plus I, you'll get 2 omega by, here omega gets cancelled and you'll get minus I is minus 2I equal to z plus iz minus 1 minus I plus z plus 1 minus zi minus I by z minus 1 plus zi minus I minus z minus 1 plus zi. See, minus into minus plus, right? You'll get zi. Minus into minus plus I. Okay, fine. Now observe and cancel the terms. I mean the numbers or terms, whatever. Here you can cancel 2. The denominator you can cancel plus z minus z and minus I plus I. In the numerator you have z plus z plus z plus iz minus iz. Cancel them. And you have minus 1 plus 1. Cancel this. And you have plus, minus I minus I, you can cancel that, right? So we'll get omega by minus I equal to z plus z. Z plus z gives 2z. Minus I gives minus 2I by zi 2zi minus 1 minus 2, right? Fine. Now let's take this minus I to RHS. We'll get omega equal to minus I into, take 2 common from the numerator, you will get 2 times z minus I by, here also take 2 common, you can go for one more step, cancel 2, we get omega equal to minus I into z minus I by, here you can change or you can just write like that, equal to minus iz minus into minus plus I square by zi minus 1. Since I square equal to minus 1, you'll get, right? Fine. You can take minus common from the numerator and minus common from the denominator and see what you're going to get. Right? Which uses 1 plus iz by 1 minus zi, or you can write this as, okay, it's fine, you can write this as iz plus 1, you can write a plus b as b plus a also, right? Fine, you got omega equal to iz plus 1 by 1 minus zi. See, verify and confirm that this is a required bilinear transformation. How you'll verify? Just substitute the values of z, you'll get corresponding omega. Okay, if you get corresponding omega by substituting every z, then that will be the required bilinear transformation. I'll check and I'll confirm. See, already in the denominator you're having 1 minus zi, right? So finish it here. It's not necessary to write the numerator as b plus a. Let it be a plus b. Okay, now let's see the verification part. Okay, When z equal to 1, we have to get omega equal to I. Let's see that. We have transformation. Substitute the value of z here, which gives us 1 plus I by 1 minus I. Now, rationalize the denominator. Just multiply and divide 1 plus I to the numerator and the denominator. 1 plus I into 1 plus I is 1 plus I whole square by a plus b into a minus b. A square minus b square, right? So we'll get 1 square minus I square, which gives us a plus b whole square is a square plus b square plus 2ab by 1. I square value is minus 1. This gives us 1 minus 1 plus 2i by 1 plus 1. Cancel plus 1 minus 1, you'll get 2i by 2. Where 2 gets cancelled, you'll get I. When z equal to 1, omega equal to I. Okay? Since I square equal to 1, we have to write here. Since I square equal to 1, right? Now when z equal to I, omega must be 0. Let's see that. Substitute the value of z here. Since I square equal to minus 1, sorry, I'm so sorry. I'm just in a hurry, so I'm making mistakes here. Fine. Is equal to 1 plus I square by 1 minus I square equal to 1 minus 1 by 1 plus 1. Since I square equal to minus 1, I'll write one more step, okay? There's nothing wrong in it. This gives us 1 minus 1 by 1 plus 1, which is 0 by 2, which is 0. Now let's see for z equal to minus 1. See, when z equal to I, omega equal to 0. When z equal to minus 1, let's see what we are going to get. Substitute the value of z here in the transformation. We'll get 1 minus z by 1 plus 1 minus I by 1 plus I. Now, rationalize the denominator by multiplying and dividing the fraction with 1 minus I. Okay, this gives us 1 minus I whole square by a square plus b square. This equals to 1 plus I square minus 2i by 1 minus of minus 1 equal to 1 minus 1 minus 2i by 1 plus 1, which is equal to, cancel this plus 1 minus 1, you'll get minus 2i by 2, which gives us minus I. So when z equal to minus 1, omega equal to minus I. Okay, therefore we have done the verification, right? So we got the proper answers. Okay, therefore 1 plus zi by 1 minus zi is required bilinear transformation. This completes the problem. So let's see the third problem. Given z1 equal to minus 2, z2 equal to 0, z3 equal to 2, omega 1 equal to 0, omega 2 equal to I, omega 3 equal to minus I. The bilinear transformation is given by omega minus omega 1 into omega 2 minus omega 3 by omega 1 minus omega 2 into omega 3 minus omega equal to z minus z1 into z2 minus z3 by z1 minus z2 into z3 minus z. Okay, just substitute the values. Omega 3 minus omega 2 minus omega 3 by omega 1 minus omega 2 into omega 3 minus omega equal to z minus z1 into z2, 0 minus z3 by z1 minus z2 into z3 minus z, right? This gives us omega into 1 minus into minus plus I by minus I into minus I minus omega equal to z minus into minus plus 2 into minus 2 by minus 2 into 2 minus z, right? You can cancel minus 2, minus 2 minus 2, and this gives us omega into I plus I, 2i, by, you have minus I, right? You can write this as, take minus common from this, and minus you have already here, or I'll show you, minus I into minus I minus omega. So you can take minus common, you'll get minus of, if you take minus common, you'll get minus 1, right? Clear? Minus into minus plus, I into I plus omega. Okay, so you'll get I times I plus omega equal to z plus 2 by 2 minus z. Okay, now cancel this I here, we'll get 2 omega by omega plus I equal to z plus 2 by 2 minus z. Now make a cross multiplication, you'll get 2 omega times 2 minus z equal to z plus 2 into omega plus I. Okay, you'll get 2 to the 4 omega minus 2 omega z equal to z omega plus zi plus 2 omega plus 2i, which gives us, now bring the terms that involves omega to LHS, you'll get 4 omega minus 2 omega minus 2 omega z minus omega z. I'll write this z omega as omega z, okay, equal to zi plus 2i. Now 4 omega minus 2 omega is 2 omega minus 2 omega z minus omega z minus 3 omega z equal to z plus 2 into I, or you can write z plus 2i, there is nothing wrong in it. Okay, let's write, okay, I times z plus 2, let it be. Fine, now take omega common from these two terms, you'll get omega times 2 minus 3z equal to I times z plus 2. From this you'll get omega equal to I times z plus 2 by 2 minus 3z. So we got this transformation. Check whether the transformation is correct or not. Okay, you know how to check it out. Okay, fine. Now we'll check and show you. See, this is the verification part. This is not necessary to write in your exams. Okay, so this shows that our transformation is correct. When z equal to minus 2, omega equal to 0. When z equal to 0, omega equal to I. When z equal to 2, omega equal to minus I. Just pause the video and try it yourself. You'll get the same values. I have shown you the solution also. Okay, you just need to try. Therefore, omega equal to I times z plus 2 by 2 minus 3z is the required bilinear transformation. This completes the problem. Now let's see the problem involving infinity. Okay, so here we have z1 and omega 3 which are infinity, right? So what we'll do is we'll just take them common. Suppose This is the bilinear transformation. I mean, bilinear transformation is given by this formula, right? So let's take W3 common because it has infinity, and Z1 common because it has infinity. Now coming to the first one, I'll show you, okay? W2 minus W3. We need to take W3 common because W3 is infinity, okay? Always a number, a small number by some infinity gives 0, okay? Remember this. Fine. Small number by infinity is 0. See, if you, the value of 1.2 is 0.5, right? If you have big number in the denominator and small number in the numerator, you'll get something like this, okay? A less number. If it is 2, you got 0.5 when it's divided, I mean when 1 is divided by 2. Likewise, infinity is a big number and the numerator will be definitely a small number because we have not mentioned anything. But this denominator is, if it is infinity, then you will get 0. Let it be. Now here you don't have omega 3 to this, right? But we need to take omega 3 common from these two numbers. So what we'll do is we'll just multiply and divide omega 3 to the first term, so that it will be easy to take omega 3 from the two terms. Okay, you'll get omega 2 by omega 3 minus 1, right? Likewise, when you have omega 3 minus omega, you don't have omega 3 in the second term, so we'll multiply and divide omega 3 to it. Now if you take omega 3 common, you'll get 1 minus omega by omega 3, okay? And yeah, this becomes omega 3 into, this becomes 0 minus 1, okay? And this gives us omega 3 into 1 minus 0, because omega 3 is infinity. A number by infinity becomes 0. Number by infinity becomes 0. Okay, just keep this in mind, okay? I'll show you again while solving the problem. Z minus Z1. Z1 is infinity and we don't have any Z1 in the first term, so multiply and divide Z1 to it. Now take Z1 common from both the terms, we'll get Z1 times Z by Z1 minus 1. This gives us Z1 times 0 minus 1. Since Z by Z1 is 0 because Z1 is infinity, a number by infinity is 0, right? Likewise, you have one more term, Z1 minus Z2. You need to take Z1 common, but here you don't have any Z1. Just multiply and divide Z1 to the second term, you'll get. Now take Z1 common, you'll get 1 minus Z2 by Z1, right? It gives us Z1 times 1 minus 0. Now coming to the problem. Since Z1 equal to infinity and omega 3 equal to infinity, the above relation becomes, or can be written as, omega minus omega 1 into omega 2 minus omega 3 can be written as omega 3. Just take omega 3 common from these two terms, you'll get omega 3 times omega 2 by omega 3 minus 1. Okay, I showed you, right? This is what I have written here, by omega 1 minus omega 2 into, here again we'll take omega 3 common, then you'll get 1 minus omega by omega 3, right? Clear. Now take Z1 common, you'll get Z1 times Z minus, yeah, you don't have any Z1 in the first term, right? You'll get Z by Z1 minus 1 into Z2 minus Z3 by, here take Z1 common, you'll get Z1 times 1 minus Z2 by Z1 into Z3 minus Z, right? Cancel this omega 3 and Z1. Fine. Now this gives us omega minus omega 1 into omega 2 by omega 3 minus 1 by omega minus omega 2 omega 1 minus omega 2 into 1 minus omega by omega 3 equal to z minus z1 minus 1 into z2 minus z3. You have to write very carefully, okay? Don't be in a rush. 1 minus z2 minus z1 into z3 minus z. Now substitute the values here. Okay, you can write w2 by w3, w by w3, z by z1, z2 by z1, 0. Just write directly 0, because we know that when the denominator is infinity and numerator is some number, you'll get 0. Okay, just write 0 directly. You get omega minus omega 1, 0 into omega 2 by omega 3, I by infinity, 0 minus 1 by omega 1, 0 minus omega 2, I 1 minus omega by omega 3. Omega by omega 3 is omega by infinity is 0 equal to z by z1. z1 is infinity, z by z1. z by infinity is 0 minus 1 into z2, I minus z3 0 by 1 minus z2 by z1. z2 is I by infinity is 0 into z3 0 minus z, right? This gives us omega minus 0 omega into minus 1 by minus I into 1 equal to minus 1 into I by 1 into minus z. Minus gets cancelled and you'll get omega into 1 omega by I equal to, or minus, better, minus I by minus z. This gives us omega by I equal to I by z. Now take this I to RHS, you'll get omega into I times I by z, which is I square by z. Since I square equal to minus 1, so you'll get minus 1 by z. Therefore omega equal to minus 1 by z. Whether it is the exact or correct bilinear transformation or not, we have to check using verification. Okay, it's not necessary to write verification part in your examination, but for our convenience we'll check whether it is right or wrong, right? So let's see how to check whether it is right or wrong. See, don't, it's not necessary to write verification part in your examination, okay? I'm just doing it for our sake. When z equal to infinity, we have transformation. We got the transformation omega equal to minus 1 by z, right? Substitute the value of z, 1 by z, which is 0, right? 1 by infinity is 0. When z equal to I, then omega equal to minus 1 by z, substitute the value of z, which is I, multiply and divide I, you'll get minus 1 into I is minus I into I square. Since I square equal to minus 1, you'll get minus I by minus 1, which is I. When z equal to infinity, omega equal to 0. When z equal to I, omega equal to I, right? Fine. Now coming to the third point, when z equal to 0, omega equal to minus 1 by z, substitute the value of z, which is 0, 1 by 0, infinity. Simply 1 by minus 1 by 0 is undefined, otherwise infinity is nothing but undefined. Okay, fine. When z equal to 0, we got infinity. Fine. So therefore, final conclusion, omega equal to minus 1 by z is required by linear transformation. Right, this is the last problem in this video. Given z1 equal to 0, z2 equal to -1, z3 equal to I, omega 1 equal to I, omega 2 equal to 0, omega 3 equal to infinity. Only one infinity we have in this problem, right? Fine. The bilinear transformation is given by omega minus omega 1 into omega 2 minus omega 3 by omega 1 minus omega 2 into omega 3 minus omega equal to z minus z1 into z2 minus z3 by z1 minus z2 into z2 minus z. So you'll write the same pattern for omega and z. Okay, don't change the pattern. Fine. Now, since omega 3 equal to infinity, so we rewrite the above relation as, we'll just take omega 3 common. We have omega 2 minus omega 3, right? We don't have omega 3 in the first term, so let's multiply and divide omega 3 to it. So it will be easy to take omega 3 common from these two terms. You'll get omega 3 times omega 2 by omega 3 minus 1. Likewise, here you have omega 3 minus omega. Here you don't have omega 3, right? In the second term, just multiply and divide omega 3. Now take omega 3 common from the first two terms, the two terms. We'll get 1 minus omega by omega 3. Okay. Omega by omega 2 by this infinity becomes 0. Likewise, omega 3, it's omega, right? It's omega. Omega by omega 3, which is infinity. Omega by infinity becomes 0. Okay, fine. Now, coming to the problem. Take omega 3 common. You'll get omega 3 times omega 2 by omega 3 minus 1 by omega 1 minus omega 2 into omega 3 times 1 minus omega by omega 3 equal to z minus z1. Here in z's there is no omega, right? Just write as it is. It's z3 minus z, okay? Fine. Now cancel this omega. You'll get omega minus omega 1 into omega 2 minus omega 3 minus 1 by omega 1 minus omega 2 into 1 minus omega by omega 3 equal to z minus z1 into z2 minus z3 by z1 minus z2 into z3 minus z. Right? Now substitute the values. We'll have omega minus omega 1 I into omega 2 by omega 3, 0 by infinity. You'll get 0 minus 1 by some number by infinity. Okay, which is 0. Omega 1 minus omega 2 I minus 0 into 1 minus omega by infinity 0 equal to z minus z1 0, z2 minus z3 I by z1 0 minus of minus 1 and z3 I minus z. Now we need to simplify it. omega minus I into 0 is 0, minus 1 into omega minus I is omega minus I minus 0 is I, into 1 minus 0 1, equal to z minus 0 z, into minus 1 minus I, by 0 minus and minus plus 1, 0 plus 1 is 1, into I minus z. This gives us minus omega plus I by I equal to minus z zi by I minus z, or take minus common from the two terms and cancel out that minus. Okay, fine. Now take this minus to RHS, you'll get minus omega equal to, minus omega plus I equal to minus zi into I by I minus z, then minus omega plus I equal to minus zi minus z into I square by I minus z. Since I square equal to minus 1, this gives us minus omega plus I equal to minus zi minus z into minus 1 by I minus z. Okay, you'll get minus omega plus I equal to minus zi minus into minus plus z into 1z by I minus z. Better multiply both sides of the equation with minus. Here itself you can take minus, or here itself you can take minus. Okay, and do. I'll show you that also. Wait. If there is a possibility of cancelling minus, cancel it out. Okay, minus of omega minus I by I equal to, take minus common, you'll get minus z of 1 plus I by I minus z. You can just cancel this minus or multiply both sides of this equation with minus. You will get omega minus I by I equal to z times 1 plus I by I minus z. Now take this I to RHS, you will get omega minus I equal to z plus zi into this I by I minus z, which is equal to zi plus zi into I square by I minus z. This gives us omega minus I equal to zi plus z into, we know that I square is minus 1. This gives us zi minus z by I minus z. Okay, see, if you multiply both sides of this with minus, you'll get the same thing. Okay, there is nothing wrong in it. Okay, fine. Good. Now we have omega minus I equal to zi minus z by I minus z. Now let's take this I to RHS, you'll get omega equal to zi minus z by I minus z plus I. Now this becomes omega equal to zi minus z plus I times I minus z by I minus z. Okay, is equal to, this gives us omega equal to zi minus z plus I into I square minus zi by I minus z. Then omega equal to zi minus z. Yeah, here you can cancel plus zi minus zi, right? Then you'll get minus z plus I square. I square is minus 1 by I minus z. Simply minus of z plus 1 by I minus z, or you can write this as omega equal to minus of z plus 1 by, you take minus common, in the denominator you'll get z minus I. Cancel this i's, you'll get z plus 1 by z minus I. Either you can write this or you can cancel minus and you can get this. So this is the verification part. When z equal to 0, omega equal to I. When z equal to minus 1, omega equal to 0. When z equal to I, omega equal to infinity. Okay. So finally this shows that therefore omega equal to z plus 1 by z minus I is the required bilinear transformation. This completes the problem. Please do carefully while solving the problem, okay? Write the values clearly. Don't be a hurry like me. I just solved every problem in a hurry. Please don't do that. Fine. Well, we have seen a few problems from conformal mapping in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.